Okay, so this is Sean Strandy. I'm here with a couple of my colleagues at San Diego Supercomputer Center. We're going to be talking about the Comet high-performance computing system, and we'll go through the motivation for that, talk about the design of Comet, give you an overview of some of the system components. We'll have Nancy Wilkins-Deere. We'll talk about the science gateway aspects of Comet. Trevor Cooper, the HPC systems manager, will talk about the high performance virtualization. We'll go into the user environment and importantly at the end wrap up with how you get access to Comet. And there are multiple ways to do that, and we'll talk about those in detail. As we go through this, we do have a chat interface open, so feel free to jump in there and ask any questions. We ought to be able to address those in real time as well. So again, this is Sean Strandy, and I'm going to give us some background over Comet. So let's just get started for a little bit of motivation. Comet is the first high-performance computing system that was specifically designed to serve what's called the long tail of science. We'll go into what that means. It's also one of the first systems to deploy high-performance virtualization. Trevor will talk about that. Designed explicitly for science gateways, and finally with some policies for allocations that favor the long tail computing, which from the user's point of view means rapid turnaround, it means easy access, and a host of other things that are critical for productivity. This next slide here, we're showing some data from the National Science Foundation XDMod database, which collects usage statistics for all of the systems that are offered to the NSF. And this particular plot, we're showing the percentage of jobs that were run on the NSF systems by core count and by how many service units or core hours were charged. So the dotted line here shows the percentage of service units charged or core hours charged for a given job size across the x-axis there. And then the solid line shows how many jobs were run. And what's interesting in this plot as I step through this is if you look at the small fraction of jobs and core hours that are consumed by the largest size of jobs, you see this is a very small percentage. So roughly 1% of all the jobs in the NSF portfolio use more than 2,048 cores, which means that the 99% of them are running on a much smaller core count than it would be typical of a large HPC system. So we designed Comet around this notion that not only is the job size fairly small, but also the amount of time consumed by those jobs is fairly small. So 99% of the jobs consume less than about 2,000 cores, and more than 50% of the total core hours consumed are by jobs of that size. So when you think about what that means, it means that the system design is going to be fundamentally different for a system like this than it would be for a large HPC system. So you'll see in these next couple of slides that this amounts to one rack of Comet. Any job in this category that we're talking about, in the 99% consuming this bulk of core hours, can be satisfied by a single rack of the Comet system. So what does that mean? Well, that means that we can have a tremendous impact on science. And so this next slide here talks about the kinds of impacts we're seeing with Comet over the last almost 2 years of operation. We've been participating in important scientific discoveries, including the detection and verification of gravitational waves, understanding the tree of life, material science, and many others. Notably, there have been over 350 publications that have cited the use of Comet directly, and this does not include many more publications that are attributed to the gateways, which you'll hear a bit more about. Another notable achievement with Comet, we've now served nearly 18,000 unique users that have come to Comet either through a traditional login that you might be familiar with, or through these science gateways, which actually provide a simple access method for unique communities, and Nancy will talk about that in just a second. Over 350 unique institutions have had allocations on Comet. We've issued almost 500 trial accounts. We'll talk about those in a minute that have been converted into full exceed allocations. And we've been tracking how our users have responded to the system, and we're seeing a lot of happy users, pleased with the usability of Comet, the throughput they're seeing, and the diversity of resources on the machine. Okay, so this next slide is just a breakdown of how these 18,000 users have shaken out on Comet. We've served about 2,600 through a traditional login, that'd be like SSH. Our first really large gateway on Comet is Cypress, this phylogenetics gateway, and this has been an extremely successful gateway for over 6,000 users on Comet, many more on other systems that Cypress has run on. The publication counts on Cypress are very high as well. Over 3,000 have cited this gateway, and so again, a lot of impact there. Recently, we added a protein structure gateway called iTassr, which has served now over 8,000 users, and then we've got a number of other gateways totaling about 1,000 users. So again, we're seeing a lot of growth in gateway communities here, and this is one of the big reasons why we're able to reach so many users with a relatively modest system. So I'm going to go into the Comet system just a little bit. This chart here is kind of a high-level picture that gives you a notion of Comet as an integrated system. That is, it's not just a high-performance computing system, but it's embedded in high-performance networks that reach into national systems and international networks, high-performance storage systems that provide both working space for running jobs as well as storage for projects that are generating data and need to subsequently analyze it. We're connected to the Open Science Grid. Here on campus, we reach into campus networks for DMZs. So Comet sits within this embedded sort of integrated cyber infrastructure. Drill down a little bit, I mentioned that we can satisfy about 99% of the jobs that are typical of researchers through a single rack in Comet. So that's a full bisection network, which means every node can communicate equally with every other node in that rack at high bandwidth and low latency. Each of the nodes has 128 gigabytes and 24 cores. These support both shared node jobs, which is a characteristic of some of our users who do high throughput or just need a few cores. And it reduces having to reach into other nodes and racks for memory. There are about 2,000 compute nodes on Comet, 36 GPU nodes, 4 large memory nodes, which lets us support, other types of computing that many users need in their workflows. Science gateways are a primary use case for Comet, which means we have specialized nodes, user services, and other resources to get those gateways up and running and integrated with Comet. Virtual clusters allow communities to build custom software and lay that down on Comet on top of our clusters, so they can bring their own applications, their own system software stack, libraries, and even databases and other service elements into the machine. And then finally, I mentioned we have high performance and durable storage, which supports both the compute, the data workflows, and we do provide some backup of critical project data into a sort of a shadow version of the project storage. Okay, so here's just another picture to give you a sense of what a rack looks like. So a single rack at Comet, if you look at the yellow here, is 72 nodes, 1,728 cores, 9 terabytes of memory, excuse me, and 23 terabytes of flash. Every Comet node has a local flash drive on it that's available as a scratch resource. Lets users do I/O, interim I/O, and avoid some of the latency issues that are associated with going to a parallel file system through its metadata server. So if you think back on that early slide about how many jobs fit into a 2,000 core bucket, 1,728 cores on a Comet rack satisfies a tremendous amount of the user need for high performance computing. So think of it as a high performance computer in a rack, and there's 27 of those. This is a bit of an eyeball chart here. This is the Comet network architecture. It just shows you how this is embedded into the overall system. So the sort of pink stuff, if you will, here in the middle is this sort of core networking infrastructure. Comet on the far left is a FDR InfiniBand system. We bridge through FDR switches and gateways into an Ethernet-based storage environment, which which is seen at the bottom in the green. And then on the far right, you can see that we're connected with through data mover nodes and high performance networks into national computing infrastructures. So we have data mover nodes that let you move data in and out of Comet's storage systems, and then subsequently access those through the machine. And then there's a number of other service nodes, of course, data movers, gateway hosting nodes, management nodes, and so forth that are used for the system. So there's some interesting details here, and for those who might be interested. Okay, so I'm going to hand this to Nancy, who's going to talk for just a second about science.
Great. Hi, everybody. Thanks for joining. So Science Gateways, probably many of you have heard about this if you're on this call, but basically web interfaces to higher end resources. And in this case, that's Comet, the supercomputer. We're seeing gateways really take off in the research space because of what they can do, how they can bring in really large numbers of communities, how they can provide access to some kind of highly specialized resources to people who are not necessarily from top tier research institutions. So you're expanding opportunities to a lot of different people, and that's quite nice. So Comet's been designed from the get-go to be gateway friendly. And you can see that. I don't know what percentage of gateway jobs in Exceed we run. The last time I looked, it was like upper 70% range. And it's because we made special arrangements with the NSF in order to allocate it in such a way that you got the throughput that you really need to be a successful gateway. So once you have a web interface, there's a certain expectation that things aren't going to sit in the queue for the week and that sort of thing. And so we really see gateways flocking here, which is great. So this is a pie chart of actual CPU use by gateways. What we'd like to see is really more and more gateways coming in and being able to do the kinds of things that that Comet has done. And I think because of the range, so iTasker, which is the orange slice that you see here, that's a gateway that just started in October, and it's a protein structure prediction gateway that has a huge user community. It's instantly more than double the number of gateway users that we have on Comet. And so that pie slice is going to start getting a lot bigger. But really what this kind of underscores is that this isn't, just a Cypress opportunity or a neuroscience gateway opportunity, but an opportunity for any gateway that has no connection to a center except that they've written a successful allocation proposal like iTasker has. What I like about this slide, it's a Cypress slide, but if you look at the types of, where it says non-governmental organizations, the types of organizations that you see listed there are not typical supercomputing using organizations. So the Smithsonian, the American Museum of Natural History, the Field Museum, Botanical Gardens, these are not your typical supercomputer users, but they have a real need for this phylogenetic software that Cypress makes available. They don't want to maintain clusters. They don't want to maintain software optimized for the hardware and the right version and all of that sort of thing. They just want to do their work. And I think the most telling statistic is the second to last bullet there, where there are real publications coming from this group as a result. So that's the really powerful thing here, that they're using this to advance science. Neuroscience Gateway is a nice example. It's a lot more individualized than Cypress is. They keep a close handle on who their users are because their users actually make changes to the codes that run. So there are these modules that are used in the neuron code where a neuroscientist can kind of tailor it to do exactly what they want to do. And so because of that freedom, they have to keep a lot closer eye on who the users are. But what's also really nice about this one is a lot of you might have heard about the BRAIN initiative announced by President Obama maybe a year and a half or 2.5 years ago now. So there's a lot of interest around brain science now and solving problems that are related to Alzheimer's, and there are calls for proposals in this area, and some of those calls say, hey, go use the Neuroscience Gateway for this work. And so you're kind of leveraging this investment that's already there, and then you're using it to, kind of leapfrog and go do your own work on top of that. And so I think that's pretty powerful too. So this is, yeah, especially with the ITASR numbers, the numbers of users are just going up tremendously. And what you see here is we've got right now, gosh, on Exceed, I think 77% of all the users were coming from gateways now that ITASR has kind of exploded on the scene. So we're seeing more people come in through gateways than we are at the command line. But what you also see is that they don't necessarily consume a whole lot of CPU time. So you see 30 million consumed by those 15,000 people, whereas your command line, astrophysicists and such are still consuming the lion's share of the resources. But if you had a column that included papers there also, I think that the interesting thing is how much a gateway user can do with very little CPU in the way of advancing their science. So there's kind of lots of things to look at here. What's nice also is in this green text box, those gateway users don't have to write in these 8-page XRAC requests where they, provide scaling results for all the codes that they use and things like that. They just create a login on the gateway and they can use those resources. So it lowers the barrier considerably to who's got access to Comet. This is an example from another project that I'm involved with. It's called the Science Gateways Community Institute. It was one of the first 2 institutes launched out of the NSF's S2I2 program. And there's a nice leverage here because what the Institute does is focus on kind of front-end gateway development and what the challenges are there and bringing a whole range of expertise that you need to design a really good gateway. And there's kind of lots of things that you need, but you only need them for little bits of time, like a usability designer or a cybersecurity expert or some advice on licensing or things like that. So we in the Institute concentrate on the front end. Comet is here designed to facilitate the back end. So when someone's got a great gateway good to go, hey, there's a supercomputer that's tuned just for gateway usage, and there's a really easy path. So it's kind of a nice leverage of a couple of different activities, and we try to promote the whole gateway ecosystem, if you will. So there's a conference every year, there's a special journal issue. Our work has spawned similar activities in Europe and in Australia, and so we kind of coordinate nicely with all those groups. And that's it. Yay. Thanks.
Thanks, Nancy. So Trevor's going to talk about high-performance virtualization and the virtual cluster interface on Comet. There, so this is Trevor Cooper talking. I'm the current manager of the HPC Systems Group and heavily involved in the development and deployment of Comet's virtual cluster capability. The reason we decided to add this capability to Comet is really to satisfy a number of different needs. One of the things that's very common with people using our system is the requirement for us to support special versions of software or alternate versions of software than what we kind of traditionally have in our default stack. And that creates quite a heavy load on our user support team and on our systems team to develop and test those softwares before providing them on the system. And in fact, there are certain software that we just choose not to deploy onto our system entirely for various reasons. And one of the common ones is that they require elevated privileges on the machine that we're just not willing to provide to the users. And so one of the big thrusts or motivations behind us creating the virtual cluster capability is to provide an environment whereby people with those specific needs are able to deploy custom software stacks onto our system without affecting other users. We kind of contain their elevated privileges within their own virtual cluster. Another motivation for virtual clusters is to try to create this capability for communities that have the expertise and ability to utilize and install clusters, but perhaps don't have the resources locally to be able to land that kind of hardware on their own floor. And so we're working on creating this capability whereby
campuses, as an example, could have someone responsible for deploying a virtual cluster on Comet, and then people at the campus might be able to apply for an exceed allocation to do their computing, and then they would be able to use the virtual cluster provided by the on-campus person on our hardware. And that's another use case that we're looking at. And the final one is looking at providing a capability for certain types of science cases to be burst onto our system to provide kind of relief for small external resources that don't have the capacity to handle those. One of the unique ways that we're doing that with Comet that's different than many other cloud provisioning type systems is that we actually provide what we call close to bare metal capability on our system. When a virtual cluster is created on Comet, the administrator has full access to the KVM virtual console for the machine. The exception of being able to program BIOS, they install from ISOs that we or they provide on our system. And it's a bit different than the cloud environment where you're using an image that you've gotten from another resource. And we'll go into some of the details now about that. So one of the things that's important for this is that again, that Comet's virtual clusters we provide a capability to give people what we would actually call an HPC virtual cluster. So you have the capability to build groups of machines in cloud resources, but typically they're not able to provide you the performance that you would typically see in an HPC environment. And what we mean by that is really going to be like the multi-node MPI, low latency type of performance that you would see on native Comet in batch system. The way we do that is that we provide or we leverage single root IO virtualization on our compute nodes to give near native bandwidth and latency performance to the virtual machines running on Comet. We use some other software tools to provide that capability, which we really are kind of hidden from the virtual cluster administrator. But one of the other really important things that we do is we kind of use our scheduler to share the Comet resource between regular batch utilization and Comet virtual cluster. What that lets us do is not dedicate part of the machine to virtual clusters and kind of waste that resource when it's not in use. And so the nodes can run either regular batch jobs or Comet virtual cluster jobs. And it's just the scheduler will allocate the resources based on demand. What that also allows us to do, and it's an issue that's kind of arisen in Exceed, is the way to account for these virtual kind of environments. There's not really an easy way to do the accounting for this kind of thing. But the way that we've implemented it is that there's an allocation that is billed for the job that underlies a KVM virtual machine. And it really takes the burden off of using any kind of other custom accounting mechanism to capture that usage. The final thing is we have an expanded team. Systems work is done here at UCSD and Supercomputer Center here, but we have a support team that we work with folks at Indiana University who have experience with FutureGrid, and they work very closely with us in on-ramping new virtual cluster users onto the Comet system. One of the highlights of Comet's virtual clusters is the Open Science Grid's use of a virtual cluster on Comet to take care of some of the work for their users on our system. The OSG team has deployed a virtual cluster on Comet, and just regular OSG jobs that would go to any other resource for OSG can land on our system and be processed there. Into the details of how we kind of provide this performance, we're using Mellanox Connect X3 cards for our InfiniBand network, and we use SROV to do to provide the virtual InfiniBand interface into the KVM guest. We use some of the security features of the InfiniBand network to segment our InfiniBand network and provide kind of secure environments for all of this software to run for each virtual cluster. And again, the thing that we focus on is that the performance for this is very close to the native performance in batch. The way this looks on our system, and again, we're sharing the compute nodes with regular batch, but each virtual cluster ends up with its own private management network, with its own InfiniBand network, and its own virtual hosts that run on different kinds of nodes. Compute nodes run on our regular compute nodes, and we have specified or specific dedicated hosting nodes where the front ends run, and they actually run kind of on a 24/7 basis. They're not scheduled through the scheduler like the compute nodes are. It provides a mechanism for the virtual cluster administrator to manage their compute nodes and provide access to the virtual cluster for their users. Again, inside the virtual cluster itself, it just looks like a regular kind of cluster that you're familiar with. There'll be a front end that is used to kind of host the software and deploy the compute nodes within the virtual cluster. Each of the compute nodes will have a local disk for storing local data on the system. All of the disk state is saved back to our storage system outside of the virtual clusters, and so compute nodes can boot and install off of their front end, but state can be saved between runs, and so they don't have to reinstall every time. It kind of minimizes the time to bring up new nodes in the environment and start sending jobs to the system. The entire InfiniBand network within the cluster can be used just for regular MPI traffic, or it can also be used for IP over IB capabilities inside the virtual cluster. Again, a focus, our biggest current user of virtual clusters on Comet right now is Open Science Grid, and some of the strengths of using virtual clusters are that the software stack that you may have to deploy into your virtual cluster doesn't have to be different than what you deploy on your own systems back home. Again, because you have full control of the system, you can deploy whatever software you want inside your virtual cluster, and it can appear just like the systems at home. So users, if they're using command line to access nodes in the virtual cluster, would use the exact same set of commands that they would use on your home interface. And it really kind of makes the deployment of this kind of a system kind of seamless for people who have that capability on other hardware already. The mechanism that OSG uses to deploy their nodes is the exact same kind of back-end infrastructure. They use Puppet to install other systems. The same Puppet servers that install the nodes in their own home cluster are used to install their nodes on their Comet virtual cluster. And it's really no different for them to manage the systems inside Comet as it is to manage the systems in their own cluster. And I think that covers it for the high-level overview of virtualization.
All right, thanks, Trevor. Now, Mahidar Tataneni is going to give an overview of the user environment, including some of the software and other features.
Hi, this is Mahidar. So I'll go into some of the setup of the traditional software on the Comet system, and also how you can get access. So before I do that, we did design a lot of our policies and our setup to basically support the long tail users, so the 99% that Sean talked about earlier. So we are basically optimizing for throughput. We set limits on the job sizes so that we don't have a few users dominating the whole system. So the limit is set to 1728 cores, which is a single rack. We also cap project requests, individual project requests, so that, again, we don't have one allocation dominating the system. We do make an exception for gateways in such cases because they represent a lot more users. So that's another thing we do. And then we also monitor the allocations and the queue wait times, and basically throttle the amount available for allocations to make sure that the wait times are reasonable overall in a given quarter. The other thing we do is we have the concept of trial accounts, where basically users can request time on a system on Comet and get a response within a day and get on the system and try out. It's not a lot of time, but it's enough to basically test the capabilities of the system and see if it works for you, and then put in a bigger allocation. As Nancy mentioned, we have a lot of science gateways on Comet, and they reach a lot of users through easy-to-use web portals. So that's another way of getting on Comet. And as Trevor mentioned, VCs, the virtual clusters are a good way to support communities. And in terms of performance, there's a very small impact on the latency. It's about 8%. And in terms of bandwidth, there's almost no impact. So you get pretty good performance of applications, even if you're running MPI jobs through the virtual cluster. It's been integrated with OSG, as Trevor mentioned, so that's one of the big VC usage cases, and then there's a lot more coming online through the pipeline. Now, that said, we still have a pretty diverse compiler, application, and library stack on the traditional part of Comet, which still is a big piece of what runs in production on a daily basis. So we have a lot of compilers, Intel, GNU, PGI, a lot of flavors of MPI, Mbappe, OpenMPI, and Intel MPI. A big and diverse bioinformatics stack, which seems to change every week. So there's a lot of new things coming online. In general, our approach is if it's open source and if it's compatible with the system, we try to install it. And the traditional fields of chemistry and engineering applications like Abacus, there's a lot of diversity in the stack. We also have a data analytics piece on Comet, which basically involves running tools like Hadoop, framework like Hadoop and Spark through the regular queue. So what we do is we have these scripts that let you spin up a Hadoop cluster once you get a set of nodes from Slurm. This allows you to basically use the local scratch on each node as the basis for the Hadoop file system. So it lets you basically take advantage of those SSDs. We also have optimized versions of Hadoop and Spark, which are more geared towards using InfiniBand at the native level. These are the RDMA versions. And there we work with the group at Ohio State to enable that. And these are highly optimized versions that can sometimes be 50% faster than the traditional setup. And again, those work through the queue too. One other thing I want to touch on in terms of the stack is we do support Singularity on Comet now, and this actually lets you customize some of your environments. It's a containerization solution, so you could say if you want to run something that works on Ubuntu, you could have an image that's Ubuntu based and install your packages in that and basically run that on Comet. This runs in user space, doesn't require much support because if you're familiar with that environment, you can pretty much install it, and you could have this image on your laptop and do all your installations there and then move the image over to Comet and run. We have about 15 groups running this on Comet right now. A lot of applications like TensorFlow, ParaView, Torch, Phoenix, they're all going through Singularity. There's a link out there for more details of Singularity if you need. We do have a small subset of nodes, about 36 of them, that are GPU enabled. So we have 2 K80 cards in each GPU node. That's 4 GPUs in total. There's a pretty rich set of software that basically uses GPUs. I mean, we listed Amber here, but there's a growing stack of chemistry and data analytics tools that are basically GPU based. So we support a lot of them, either directly or through Singularity in the case of TensorFlow and Torch. As I mentioned, we favor small allocations and gateways. So we are trying to basically get to as many users as possible. So we are the individual PI allocations are limited to 10 million service units. This allows us to basically hit more people with allocations. As I mentioned, SANS gateways are an exception. They can apply for more than 10 million SUs since this actually impacts a much wider group of people. And also in the allocations process, if there is a need to reconcile some of the allocations to cap them, then gateways are preferentially given the impact. In terms of how to get access, lots of different ways. One requirement is that the principal investigator on a project should be either a researcher or an educator at a US-based institution. You can have foreign collaborators, but the PI needs to be at a US institution. The quickest way to get on Comet, if you don't have an account already, is to request a trial allocation, and we give you 1,000 hours, and we try to respond within 1 business day, and it's a quick way to get on the system and try things out. Also, there are campus champions at a lot of US institutions that can that have allocations on Comet, and they can add you to the allocation. So where to get on if you're at a US institution. Apart from these 2 quick options, there's also a smaller allocation, the startup allocation for 50,000 hours, which for most people might cover their research, which is a pretty short allocation request, about a page, and typically they're turned around in under a week, and that's another way to get on the system. And this has an advantage that if you have a group, you can add a lot of people to that allocation. Whereas the trial allocation is single user. Then in terms of going further, once you have a startup and you've tested the code and scaled out, and if you figure out that you need a much larger allocation, there's a quarterly cycle for research allocations, which are much larger, and these can go up to 10 million SEs. A service unit is a 4 hour. We also support a lot of classes on Comet, so you can apply for education allocations, and this is useful if you are, say, planning for a class in the next quarter or semester. You can apply for an education allocation. We do reservations to support classes. Like, for example, if there's a project due, we try to match reservations so that students don't have to wait a lot of time in the queue. If you contact us in advance, we try to make sure that the software stack you need is available, or at least give you a solution that works on Comet. So those are the different ways. I think at this point, I'll give it over to Sean and we can take questions.